All right, hello and welcome. Today, we're going to put on our detective hats to solve a really classic programming puzzle. Our mission, should we choose to accept it, is to find the longest symmetrical pattern. A secret message that reads the same forwards and backwards that's hidden inside any string of text. So let's start the investigation. Okay, so let's kick things off with a little warm-up. What's the longest secret pattern you can find in the word race car? Go on, think about it for a sec. Yep, you got it? It's a bit of a trick question. The answer is the whole word. Race car is a perfect example of what we're hunting for today, a palindrome. So here's our game plan. Our investigation is going to follow 5 key steps. First, we'll define the palindrome puzzle. Then, we'll uncover the center-out secret. After that, we'll dive into investigating both odd and even symmetry. And finally, we'll measure just how good our method really is. All right, first things first. Like any good detective story, our investigation has to start with a crystal clear understanding of the problem. We've got to know exactly what we're looking for, right? We need to define our case and define our clues. So here it is, our official mission briefing, straight from the source. Given a string S, return the longest palindromic substring in S. It sounds pretty simple and direct, right? But inside this little sentence, there are 2 really key terms we absolutely need to nail down. First up, our primary target, the palindromes. You know these words, like madam, level, or our old friend race car. They've got this perfect symmetry, where the letters are just a mirror image of each other around a central point. That is the exact pattern we're hunting for. And the second key term? Substring. Now, this is just a way of saying a piece of the original string that's, well, unbroken. It has to be a continuous sequence of characters. So, for example, in madam, damn is a totally valid substring. But what about ma'am? Nope, not a substring, because you'd have to jump over the D to get it. So we're on the lookout for a continuous, symmetrical sequence. Okay, so we know our mission, but how in the world do we actually solve it? I mean, we could try the brute force way, right? Just check every single possible substring. But man, that would be like trying to interview every person in a city just to find one suspect. It's just slow, super inefficient, and honestly, not very clever detective work. Seriously, just picture a really, really long string. The number of substrings you'd have to check would be absolutely enormous. A good detective doesn't waste time chasing down dead ends like that. We need a smarter strategy. We need a breakthrough, a core insight to guide our search. And here it is. This is the aha moment. What if? What if we just flipped the whole problem on its head? Instead of checking a bunch of random substrings, what if we started with an assumption? Let's assume that every single character, or even the space between characters, is the potential center of a palindrome. And from that center, we just expand outwards, checking for symmetry. It's a simple idea, but this insight, it's the key that unlocks the whole case. So this new strategy means our investigation now splits into 2 different paths, all based on what the center looks like. First up, we're going to hunt for those palindromes with an odd number of letters, like ABA or race car, where the center is one single distinct character. So for this first case, we're picturing a palindrome that has one letter sitting smack dab in the middle. Our strategy is simple. We pick a character, we say, okay, you're the center, and then we just see how far we can stretch outwards from there while keeping everything perfectly symmetrical. Let's walk through the steps. First, we pick a character to be our potential center. Then we create 2 pointers. Let's call them left and right, and we stick them both right on that center character. Now for the fun part, we expand. We nudge the left pointer 1 step to the left and the right pointer 1 step to the right. Then we ask, do the characters they're pointing at match? If they do, boom, we found a palindrome. So we do it again and again. Just keep expanding as long as those characters match and we haven't run off the ends of the string. Okay, that handles the odd ones, but what about palindromes like ABBA or noon? These guys have an even number of letters, so there's no single character sitting in the middle. Their center is more like an invisible point, right between 2 characters. So this is going to require just a small tweak to our investigation. And this is the beauty of it. The change is so simple. For the odd ones, like ABAP, our pointers start on the exact same spot. For the even ones, like UBBA, they just start out as neighbors, one on character I and the other on I+1. That's it. That's the only difference. Everything else about how we expand and check stays exactly the same. So yeah, the procedure is almost identical. We pick that potential center that's between 2 letters. We put our left pointer on the character to the left and our right pointer on the character to the right. If they match right off the bat, awesome, we've already found a palindrome of length 2. And from there, we just start expanding outwards, hoping to find an even longer one. Okay, so here's how we put it all together into one master plan. We just loop through the entire string from the very first character to the last. And at every single position, we run both of our investigations. We check for an odd-length palindrome centered right on that character. And we check for an even-length palindrome centered between that character and the next one. All we have to do is keep track of the longest one we've seen so far. This two-pronged attack guarantees we check every single possibility. There's no way the longest palindrome can escape us. And just like that, our detective has cracked the case. The method works, we'll find our answer. But, you know, a truly great detective isn't just correct, they're also efficient. So the question is, how does our center-out approach really stack up when we look at performance? Let's break down the performance review. First, time complexity. It comes out to O of n squared. Now, what does that really mean? Well, think about it. For a string with n characters, we have roughly n possible centers we have to check. And for each of those centers, our expansion could, in the worst-case scenario, travel across the entire string again. So you get something that behaves like n times n. But now for the good news, space complexity. That's O of 1, or constant space. And this is a huge win. It means that no matter how ridiculously long our string gets, the amount of memory our detective needs doesn't grow at all. We just need a few variables to keep track of our pointers and the result. It's incredibly memory efficient. And that's really the main takeaway here. I mean, sure, O of n squared might not sound perfect, but you have to compare it to the alternative. It is a massive improvement over that brute force method we talked about. We basically went from a slow, clumsy, exhaustive search to a clever, targeted investigation that gets the job done and does it elegantly. So there you have it. Our symmetry detective has successfully closed the case. This center-out method is a really brilliant piece of algorithmic thinking, but it does leave us with one last nagging question. Is this the best we can do? Could there be an even more genius method out there? A legendary detective algorithm that could solve this whole puzzle without ever having to look back? Something that could do it in just a single pass? Well, that's a mystery for another day.